everybody, welcome back to Monte Carlo methods. When we last left off, we were talking about random number generators. A random number generator is some method that's going to produce a list of numbers for you that are going to act as realizations or observations of a continuous uniform 0-1 random variable. Not only that, but the observations are supposed to be IID, one of those I's standing for independent. So not only should the values you get be mimicking uniformity in that if you were to make a histogram of them, you would see sort of equally likely output between 0 and 1, but the value should act independent. So in the last video, we talked about three main methods for random number generation. We talked about, very briefly, physical random number generators or true random number generators, which harness true randomness from the universe and try to turn them into numbers. We talked even more briefly about quasi-random number generators, which are not really true random number generators at all. They're more concerned with filling in gaps in an interval, like an interval from 0 to 1. They're concerned with the equidistribution problem, which you will see in today's video. And then finally, we talked about pseudo random number generators, which is what today's video is about. And these are algorithms in software. So you plug in a number and it performs some operations, and you get out a number. And then you plug that number in and perform the same operations and get out the next number. And it's completely deterministic, completely not random, but if you do it well, you can kind of fake it. So people have been trying to generate randomness since the beginning of people. If you go to any museum of natural history, you are highly likely to come across at some point in your journey a display of 3,000-year-old dice or bones with symbols on them that were used as dice. People care about randomness, and we, especially here in Monte Carlo methods, do, so that we can throw those darts to do those Monte Carlo integrals and other tricks we're going to learn about this semester. In today's video, I'm going to restrict our discussion to two random number generators. One, the linear congruential random number generator, which I would say is the first random number generator in modern computing, so circa 1950. And then we're going to talk about the Mersenne twister, which is the most popular random number generator in use as of the filming of this video in January 2025. I think after this video, you'd be able to code a linear congruential random number generator, but you wouldn't want to. You don't need to do this anymore. You certainly want to use something built in and probably a better random number generator. And at the end of this video, I do not think you'll be able to code the Mersenne twister because there's a lot more that needs to be said. I'm going to hit on some highlights and only hopefully make it readable to you if you do care to go look up the Mersenne twister algorithm in more detail. So random number generators are the basis for everything we do in here. You would think I'd give it a lot of weight, but it's sort of its own course. So I want to give it 30 minutes max here today. And then going forward, never talk about this again. We're going to assume we can generate random numbers and then do everything we want to do all semester when we learn about Monte Carlo methods and kind of not give random number generators their due. So just to feel better about myself, I'm going to talk about these two. Let's get going with the linear congruential random number generator. This was first proposed by Derek Lemur in 1949. It relies on modular arithmetic. Just in case you don't know or need a reminder, if b and m are integers, then the quantity b mod m in parentheses like this is the remainder in the division of b by m. When you're dividing it in, seeing how many times it can go in as a whole number, you're left with some remainder, and that's what b mod m represents. So for example, 7 mod 2, 2 goes into 7 3 times, nice and easily, for a total of 6, leaving you with a remainder of 1. So 7 mod 2 is 1. We usually think about, or most people usually think about modular arithmetic with integers only, but we can talk about 7.2 mod 2. 2 goes into 7.2 evenly 3 times for a total of 6, leaving us with a remainder of 1.2. So 7.2 mod 2 is 1.2. Just a couple more quick examples. 7 mod 9. 9 does not go into 7 as a whole number evenly at all. So it goes in 0 times, and we're left with a remainder of 7. So 7 mod 9 is 7. And finally, 8 mod 4. 4 goes nice and evenly into 8 twice, leaving us with a remainder of 0. So 8 mod 4 is 0. So there's your brief starter course in modular arithmetic if you haven't seen it. So to run a linear congruential random number generator, we need to pick some parameters. And much of the work in linear congruential random number generators for decades has been the search for best parameters. We're going to need 4 parameters. The first is known as a modulus. It's an integer parameter, usually denoted by the letter m, and it is a positive integer. The second parameter, often known as a multiplier and often denoted by the letter a, is going to be an integer taking the values either 1, 2, 3, up to m minus 1. A third parameter, known as an increment parameter, is usually denoted by a letter b, and this again is an integer, and it can take on the value 0, 1, 2, 3, up through m minus 1. And finally, the fourth parameter is something to get us started. It is a seed to the algorithm. For reasons that will become apparent in just a few seconds, we're going to denote this seed by x naught or x sub 0, and this should be an integer taking the values 0, 1, 2, up through m minus 1. So you have to choose one of those values. Now, once you have these parameters set up, you can run your linear congruential random number generator. It's a simple recursion that looks like this. So you take your current value, whether it's the seed or maybe you've already gotten going, and so you have a value at time n, or at, let's say, n minus 1, and you multiply by a, you add b, you compute that, and you mod out m, and that is your next value. So here's the recursion right here, and you keep going like that. You take your new value, multiply by a, add b, take that total there, and mod out m, and that is your next value. And you get a sequence of integers, which is not exactly what we want. We want real numbers between 0 and 1. It's easy to see, based on how modular arithmetic works, that all of the values produced in this sequence, the x1, x2, x3, etc., are going to take on values potentially 0, 1, 2, up through m minus 1. So we could divide everything by m, and we'll have numbers between 0 and 1. You might also want to argue that you could divide by m minus 1. That's a possibility as well. But for linear congruential random number generators, we divide by m. So once you do that, you'll never get the value 1 because everything is less than m, but you never get the value 1 exactly when looking at a continuous uniform random variable on the interval from 0 to 1, because it's a continuous random variable and won't actually land on that endpoint. So typically we divide by m, and then we have our output, which I'm going to call U1, U2, U3. These are the uniform observations or uniform draws, and U sub I is defined to be x sub I divided by m. Let's do a silly little example. I'm going to choose some parameters, m equals 5, a equals 2, b equals 1, and x naught equals 0. Let's produce x1. I'm going to take a times x naught plus b, so that's 2 times 0 plus 1 for a total of 1. I'm going to mod out 5. The result is 1. And now I'm going to compute x2. x2, I'm going to take a times x1 plus b, and that's 2 times 1 plus 1 for a total of 3. I'm going to mod out 5 and get 3, and so on. So when I compute x3, I get 2. When I compute x4, I get 0. See what's going to happen here? When computing x5, I just plug in x4. It's like I'm starting with the seed all over again. And this sequence is going to start repeating. Now, as a final step, I'm going to divide everything by 5. I get the output, not including the initial seed, of 1/5, 3/5, 2/5, 0. 1/5, 3/5, 2/5, 0. This is absolutely horrible. These are supposed to look like IID draws of a uniform 0, 1 random variable on the interval from 0 to 1. First of all, we're missing a whole lot of real numbers between 0 and 1. Second of all, they look really, really dependent. This is terrible. But if we have better choices for parameters, we actually could get decent results. Not only results that look better to our eye, but results that are going to pass statistical hypothesis testing for uniformity and independence. Note that any linear congruential random number generator has period less than or equal to m. We already noted that the only possible values that could come out are 0, 1, 2, up through m minus 1, and then divide all those by m. But we don't necessarily get all of those values. As you can see in the example we just did, we never got the number 4, for example. So with m equals 5, we could potentially get the number 0, 1, 2, 3, 4, and then divide everything by 5. But in our case, we never even saw the 4. So the period is not guaranteed to be 5, which would be 0, 1, 2, 3, 4. That's 5 numbers. Counting 0, 1, 2, 3. I'm just going to leave my fingers out of this and probably do better. So 0, 1, 2, 3, 4 is 5 numbers. But we're not even guaranteed to see all of those, as we saw in our example. But one thing we can see is that we want to choose m to be large if we don't want things to start repeating like this. That's certainly one way, having this repetition, to get a lot of dependence in your sequence if it just keeps repeating. That is certainly dependence. There's other ways to see dependence even if it wasn't repeating. but we want to choose M large. And in the 1970s, there were dozens of PhD theses written by people, 200 pages plus, on good choices for these parameters, A, B, M, and sometimes X naught, which was not as often put into the mix of things you need to choose wisely. And I think there was a fair amount of mathematics in those dissertations, but a lot of it was empirical results over and over and over again, people looking at different combinations for these parameters and ultimately deciding on things that people would implement or software would implement so that you would end up implementing it whether you knew it or not from some built-in random number generator. There's a really famous example, which was a linear congruential random number generator by IBM called Randu. Now, a linear congruential random number generator is a linear congruential random number generator. There aren't different ones. But what I mean by this is they had a prescribed set of parameters. They took M to be 2 to the 31, which is quite large. And at the time, because this was the late 1960s, with 32-bit computing, this was about as large as they could get. They chose A to be 2 to the 16th plus 3, B to be 0, and they recommended that X naught, the seed, be any odd number. So Randu was built into many software packages, and I'm mostly thinking about numeric and scientific software packages, but almost any software has a need for random numbers, even if it's not that obvious to you. And their random number generator was in use for 2 decades, but after 1 decade, someone noticed something. So what I did was take the linear congruential random number generator recursion and these parameters here and generated my own values. I generated 100,000 values. And do those look uniform? Do they appear to be independent? Let's look at uniformity. We talked last time about maybe making a histogram. Here's my histogram of 100,000 uniform draws using Randu. And you can see I have density on the y-axis, just like we talked about last time. And I have the uniform 0, 1 PDF across the top, which is this flat line. And I think this looks pretty good. You might key in on this gapping over here, but I think that is sampling variability. So if you're trying to test something like this, even just by eyeball, as we are right now, you certainly want to generate a lot of values, right? If you have a coin and you're trying to figure out if it's a fair coin with probability of heads being 1/2, and you flip it 3 times and you get heads, tails, heads, I wouldn't walk away and say the coin is biased towards heads, would you? So we need a lot of data to make these decisions, and that's why I generated 100,000 values. And there's gapping here, so there's still sampling variability in 100,000 values. If you were to throw out all these values and generate a new 100,000 values, I don't think you'll see that here, or you may see it somewhere else. If you were to repeat that over and over and over again, generating completely fresh samples of 100,000 values and make a histogram every time, if you saw this gapping always on the right side, now maybe I'd worry because I'm seeing something systematic. But otherwise, I think this can be accounted for. I think this is fine due to sampling variability, and this is something you get used to seeing over time. So I'm going to take my list of 100,000 values, and I want to look at these a little bit differently. So I'm going to take my first and second value, U1 and U2, and make an ordered pair, plot that point in the XY axis. Then I'm going to take my next 2 values, U3 and U4, make an ordered pair, plot that point. I'm going to fill up the cube or from 0 to 1 on the X and Y axis in the plane. And what do you expect to see if everything is working correctly? Certainly you don't want to see any patterns. You would just like to see a cloud of points. And here's what I got. Again, this is just an eyeball test. We're not doing anything formal. I think this looks pretty good. The human eye has a tendency to hone in on clusters. So you might think you're seeing clustering. Again, based on my experience, for decades, I think this looks fine. This is also, again, not a formal test, but as a first pass, not bad. I am going to try this a little bit differently. And here's what someone did back, I don't know, probably between the 70s and 80s. Someone decided to make a plot like this, but look at 3-dimensional points. So if I take U1, U2, and U3 and make that into a triplet and plot that in 3D, and then U4, U5, U6, and so on, make a nice cube, 0, 1, 0, 1, 0, 1 on the XYZ axis. What do you expect to see? I did it, and here's what I've got. This looks pretty good, actually. You expect to see nothing special, just a cloud of points. You might think for a moment that the points are thinner out here at the edges and less, dense. So like they're clustered towards the center or something. They're not. What's going on here is this particular angle I'm looking at for this cube. There's very little depth out here on these edges, but when we look through at the center, we're looking sort of the deepest way possible through the cube. So we've got points layered on points into the screen. And that's why it looks so clustered in there, because it's not. So let's try to get a better look and rotate this. So this all looks pretty good until it doesn't. Do you see that? We are missing a lot of points in this cube. And it appears that we could run our algorithm until the end of time and we will never fill these gaps. That's the equidistribution problem that we were talking about when that the quasi-random number generators specifically look to fill gaps like this. They're algorithms that specifically try to make sure the space is covered. But the original histogram looked good. And in fact, in the 60s and 70s, all the normal statistical hypothesis testing for uniformity and independence were tried and passed. And everything looked good and people used it for a long time and felt good about it until someone happened to look at it this way and, well, was startled. I'm startled. Aren't you startled? You may have heard of George Marsaglia. He's a very famous American mathematician, and he has so many great theorems to his name, but one actually has his name on it. It's known as Marsaglia's theorem. And Marsaglia proved that if you were using any linear congruential random number generator and you had your modulus parameter m, and you plotted them as n-dimensional points, so in our picture right now, it's 3-dimensional points, that you are definitely going to be restricted to a number of hyperplanes. Now, if you were going to be restricted, you would like to have a lot of planes. You'd like to fill out this cube. Marsaglia proved that at best, you're going to get, so the most hyperplanes you can get is m times n factorial, all raised to the 1 over n. And then you could put a floor function on that to make sure you get an integer, so round down. And that's the best you can do. This is a cool theorem, but this is not a sharp bound. I can't remember off the top of my head here, but in our case, with n equals 3 and m equals 2 to the 31 in Randu, this number is about 2,333, 2,334, something like that. So that's the best we can do. We can hope for that many hyperplanes, but we're actually only seeing 15. So this is definitely not a sharp upper bound on planes. Still, you are going to have this problem for any linear congruential random number generator, but they were the main source of random number generation by computers for a long time, and I wouldn't be surprised to find them in some software packages, not the heavy-duty scientific numerical things like Python, and but I'm sure that linear congruential random number generators are still floating around out there. Okay, so the second and final random number generator I want to talk about today is the Mersenne twister. You might recognize the name Mersenne from Mersenne primes. Mersenne was a French mathematician. He was around from the late 1500s to mid 1600s. He certainly had nothing to do with this algorithm because he was not around in the era of modern computing and random number generators. But you may know of him from the Mersenne prime. A Mersenne prime is a prime number of the form 2 to the n minus 1. And there's a parameter, actually the period of the Mersenne twister is a very, very large Mersenne prime, and that's how his name got attached to the algorithm. The Mersenne twister is known as a twisted, generalized feedback shift register generator. It was developed by Matsumoto and Nishimura in 1997. Their algorithm was gaining traction well before their paper actually appeared in publication in 1998. It is fast and has an extremely long period before you start seeing repetition. The period is actually 2 to the 19,937 minus 1. You guessed it, this is a prime number, a Mersenne prime, hence the name Mersenne twister. In my opinion, and my opinion only, the Mersenne twister is not at all an intuitive algorithm. it is doing strange things, and they probably tried strange things to address specific flaws that existed in pseudo random number generators at the time in the mid-90s. In particular, it really went after that equidistribution problem. So if you run the Mersenne twister out until the end of its period, if you generate those 2 to the 19,900 and whatever it was numbers, and you take a cube in a really, really, really high dimension, not a 3-dimensional cube, but up, 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 and you split that cube into very, very tiny equal subcubes, and you plot all the numbers in your cube, you are guaranteed to fill each subcube with an equal number of points if you run out the random number generator to the very end of its period. So perfect equidistribution in that sense, and no one ever gets to the end, but it's perfect in that sense. The Mersenne twister is a really popular algorithm that, as of today in January 2025, is the default random number generator in many popular scientific software packages. It has a really long period. It passes most, if not all, of the statistical hypothesis tests for uniformity and independence. It has great equidistribution. We don't get gaps in whatever space we may be working in. It is really, really fast. One of the reasons it's so fast is that it uses binary arithmetic. Now, I don't want to insult anyone, but I've learned that I believe my audience here can be quite general. So let me just say really quick, the number 23 as a decimal number. In binary, this is written as 1, 0, 1, 1, 1, and these ones and zeros represent coefficients on powers of 2 that you can add together to get 23 back. The 1, 0, 1, 1, 1 means that you get 1 times 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 squared plus 1 times 2 to the 1st plus 1 times 2 to the 0. Add that up, you'll get 23. By working in binary, there's lots of operations in math that we can make a lot faster. Just as an example, this isn't one we necessarily are going to be using in the Mersenne twister, but if you want to multiply the number 23 by, say, 2 to the n, then you can do that by just taking this decimal number and sliding it or shifting it n spaces to the left and putting in some trailing zeros. So what I mean is you would get the number, if n was, say, 3, 23 times 2 cubed, take your 10111, shift it so that you have 3 new spaces on the right and put in zeros. If you work out what this is in decimal, it's exactly what you get if you took 23 times 2 to the 3. This is known as a left shift operator, and it's usually denoted by this double caret sort of thing going on. So again, at the end of this video, I'm not sure you could run your own Mersenne twister, but if you want to read about it, and I would recommend the original Matsumoto and Nishimura paper, it's quite readable. There are other tutorials out there, but you're going to see symbols like this. And so I want to make that paper more readable for you. That's kind of my goal here. So I'm leaving off some details. For example, usually you're working with a fixed number of bits, so you can't just push them to the left without things falling off one side or the other. So there are some things to take care with here, but this is the basic idea of a left shift operation. We're going to see a right shift operation in the actual Mersenne twister today, and the carets are going to be going to the right side. And that means we're going to sort of take our binary number and push it to the right so things sort of fall off the end and put in some leading zeros. And a right shift operation, if you were to shift the decimal number 23, 3 to the right, what you're going to get is basically division by 2 to the n rounded down to the nearest integer. But I digress. I really didn't want to get this much into the weeds of the Mersenne twister. So let's move on. There are tons of parameters in the Mersenne twister. I'm not even going to list them because they're not going to make sense without really getting into those weeds. But one parameter that's going to come up a lot for us that's super important is a word length parameter. This is going to be a number that we're going to denote by a lowercase w, and this is your number of ones and zeros that you're working with in any of your binary numbers. This is usually taken to be 32 or 64, and our binary numbers that we're working with for the Mersenne twister, if you imagine the binary number of, say, 32 digits of ones and zeros sitting out, I'd like you to think of those as a column vector that has been transposed. So the state of the Mersenne twister is going to be a binary number that we're going to call xn, like the nth state. Not exactly, I'll see something about states later, but xn with a vector on it is going to be a column vector of a bunch of ones and zeros that we'd like to look at laid out like we're used to seeing a binary number. So it's going to be a column vector transpose, and I need something to call the components of this vector. So you might think, I don't know, I might, as a mathematician, I might think xn1, xn2 up through xnw, but there's two things we do a little differently here that come from computer science. One is a zero-based indexing, so we're going to start with 0, not 1. And the other is we're going to sort of count down from left to right here. So xn vector is going to be xn comma w minus 1, xn comma w minus 2, all the way down to xn0, and then that thing transposed. These are the ones and zeros. The ones and zeros on this left end here are known as the most significant bits of the number, and the ones and zeros down on this right end here are known as the least significant bits. This is going to become important when we describe the Mersenne twister, because one of the ways it really twists things up and makes itself so different from things like linear congruential random number generators is you produce a sequence of these like 32-bit numbers, and every once in a while you'll take some of the top of one of the numbers and some of the bottom of another vector and concatenate them to make a new vector, really mixing things up and twisting things. Note that we don't actually want binary numbers, right? We want realizations of continuous uniform random variables between 0 and 1. So the largest possible number you can get out of this, if you have a word length of w, is to have all ones in this binary number that would correspond to the decimal number 1 times 2 to the w minus 1 plus 1 times 2 to the w minus 2, etc., down through 1 times 2 to the 0. This is a finite geometric sum, and if you care, take a moment and think about that. This is going to add up to 2 to the w minus 1. So when you run the Mersenne twister, you don't actually do this. This is being done behind the scenes by whatever software you're using. You'll get a binary number. You can transform it into a decimal number and ultimately divide by 2 to the w to get those numbers between 0 and 1. So we've talked a little bit about notation. How does this algorithm work? What is the flow of the algorithm? You have to start it with a seed vector x naught. And this is going to be a w by 1 column vector of ones and zeros that has to be fed to the algorithm. Generally, you're not doing that as a programmer. You're getting it from some internal clock. We will talk about seeding random number generators in here. So there's some given binary vector. And you fill out an entire seed matrix. So actually, as this algorithm goes, each state that's produced is not just one vector at a time, but an entire matrix. This matrix is w by in general n, but n is usually taken to be 624. Again, check out the original paper for some of these numbers. But this is w by n. Each column is going to be produced from the previous column to fill out an entire matrix that is actually seeding this algorithm, where we're going to produce then another w by n matrix. To fill out these columns, I'm going to keep this probably too brief because I'm running out of time and I'm not giving you enough detail to run it on your own anyway. But the ith column vector is going to be a constant c. Actually, let me skip ahead in here. The ith column vector you're going to take here is the I minus first column vector, and this is a right shift by w minus 2 bits. W being the word length, which is usually 32 or 64. It's really important in these operations here to keep your word length the same at all times. So you don't just want to dump bits off the end or add in bits. You're going to have to compensate on the other side of your vector. But again, I digress. So this is the I minus first vector right shifted by w minus 2 bits, and then you add it to itself, its original self, the I minus first vector. This plus sign with a circle around it is known as bitwise or mod 2 addition. So you're adding ones and zeros, and if you ever get 2, then mod 2, that goes back to 0. In the end, you multiply by a constant c and you add an I, and everything stays mod 2 so that your result is zeros and ones, and that is how you get the next vector as you recurse across the vectors of this initial seed matrix. Okay, so let's finish this off. I'm definitely running out of time now. I said we're going to keep an entire matrix at a time. The one we just created was called state 0. We're going to produce a state 1, a state 2, etc. Those are all going to be w by n, w usually being 3264, n usually being 624. And there's a recursion here as well. I just want to focus on this one column right here, the first column of state 1, xn. So we have a weird looking formula here. Xn you're going to get by taking k equals 0. This formula, we actually run k over 0, 1, 2, up through n minus 1. You can see that I've got bitwise mod 2 addition here. This vector here comes from a column of the original matrix. This M index is a parameter of the model. It's something that needs to be chosen beforehand to tell you what column of the original matrix to choose in order to build this first column for your state 1 matrix. What are we adding to this? Just look at this thing in parentheses. This vertical line is a concatenation operator. And so this xk with a u up here is a number of upper bits from the xk vector. And this xk minus 1, with this is an L up here, I know my handwriting's not that great, is a vector of least significant bits of a vector from the state 0 matrix. And in particular, we take w minus r of the most significant bits, where r is, guess what, another parameter that is given in the paper, and r least significant bits of another vector, so that in total, when we concatenate them, this is a vector of length w. We're going to multiply it on the right by a w by w matrix A, which is another parameter. So you get to choose A as well, but some choices are much better than others, and some choices allow you to avoid matrix multiplication completely and turn this matrix multiplication into just another shift operation. So you add these mod 2 to this other guy, and you produce xn, and then you let k equals 1, and you have a formula to produce xn plus 1, and so on. And definitely not something, as I said, you could walk away with. You can walk away from here in program, but I hope it's readable now to you if you want to take that time. And if there is demand, I guess, put it in the comments, and maybe I'll make a full Mersenne twister video. But personally, in this course, I'd like to get on to what I think is the good stuff, the Monte Carlo stuff. Oh, by the way, I forgot to mention there's an additional step. After you produce the state matrices, there's a tempering step, which is purposely there to improve equidistribution. And you basically are multiplying each vector by another matrix known as a tempering matrix. It's a W by W matrix. If you're trying to read the paper, it'll be denoted by a capital T. Now, as of today, which is in January 2025, the Mersenne twister is the default random number generator in Python, in R, in MATLAB, in C++. Very recently, I could be wrong, but I think like in the last year, languages like Julia and Mathematica, Wolfram Alpha have started to use their own proprietary random number generators, but they certainly use this for a long time and certainly still include it, just not as the default random number generator. So it's more likely than not that you are going to be using this, whether you know it or not, depending on what software you're choosing to follow along in this course. As mentioned in my previous video, in this course, I've been requested to use R, and the Mersenne twister is currently the built-in random number generator in R. In fact, in the next video, we're going to open up R. We're going to generate some random numbers. We're not going to do all this modular arithmetic. We're just going to use a one-line expression to grab some uniforms, but we're going to make sure we can make that histogram and put that PDF on top and make sure things look good. And then also in the next video, we're going to start talking about formal statistical tests for uniformity and independence. So I really hope to see you in the next one.